Okay, let's give you guys some more practice. So establish if this series will converge or if it will diverge. So press pause and have a go. Okay, so to do this, the first thing to do is you check. The first thing to do is you check that the limit of this, as n moves from 1 to infinity, check that the limit equals 0. So as n moves from 1 to infinity, here you've got n to the power 3 plus 1, so n to the power 3 plus 1. As n moves towards infinity, this is going to be very, very big, and then you're adding a tiny amount onto it. So let's just consider this n to the power 3 plus 1 as n to the power 3. And then here you've got to square it. So that would be n to the power of 6. And then up here you've got n squared. So as n moves from 1 towards infinity, then you can see that the denominator is going to be much, much, much bigger than the numerator, meaning that overall, as n moves from 1 to infinity, overall this thing here will head towards 0. The limit of this, you can just glance at it and see that the limit will be 0. So this is good. If the reason why we're doing this check is that if the limit is anything other than 0, let's say 9, then if the limit equals 9, then you will immediately 100% sure that this is going to diverge. But because it's 0, there's a chance that it could still diverge, and there's still a chance that it could converge. If it's anything other than 0, let's say 7, then you will be 100% sure it will diverge, and then your problem's done. This thing here will diverge. But here, because it's 0, there's still a chance that it could diverge. There's still a chance that it could converge. So now that this is done, we now want to make use of that theorem where we would compare this with this. So there's a theorem that says that you can compare this with this, and that theorem says that if this thing here diverges, then you will immediately know that this thing is going to diverge. If this thing here converge, then this thing here will also converge. That's a theorem that says that. But in order for you to apply that theorem, you need to check these three. So you need to check that this thing is continuous in the domain from 1 to infinity. So let's check if it's continuous. So is this thing continuous? You asking the question if it's continuous, it's really you asking when will this thing break down. Well, it will break down when the denominator equals 0. So when will the denominator be 0? Well, in the domain from 1 to infinity, it will never be 0, because in the domain 1 to infinity, this thing here will never be 0, and then you square it, it will never be 0. So it's continuous. It doesn't really break down in the domain from 1 to infinity. So this is good. So the next thing is it always positive? Well, is this thing always positive in the domain from 1 to infinity? Well, this thing will, glance at it and think about it, it will always be positive. Is it always decreasing? Well, earlier we said that this thing, the denominator, will be much, much bigger than the numerator. So as you move from 1 to infinity, it is going to be decreasing. Or if you're not convinced, then you can differentiate this, and then check that in the domain from 1 to infinity, the gradient is always negative, meaning it's always going downhill. But you can tell that it's decreasing by just glancing at this. Okay, so this is good. This is good. So this is good. Because all three have been satisfied, then we can apply that theorem. We can apply that theorem where it says that if this thing diverges, then this will also diverge. If this thing converge, then this thing will converge. So now it really boils down to us determining whether or not this will converge or if it will diverge. So let's use improper integral. Let's integrate this. So using improper integral, we now need to integrate this. If you integrate this, it will give you this. Now to integrate this, you could use substitution, but learn to do it just by glancing at it. So visualize this as this. Hang on. Visualize it as x to the power 2, and then visualize this thing here as this. Hang on. X to the power 3 plus 1 to the power minus 2 to the power minus 2. So visualize this whole thing here as this. So when you're integrating, try to keep an eye out for something that is the exact derivative of another thing, or near enough the derivative. For example, this thing here happens to be, well, it happens to be near enough the derivative of this whole thing, because if you differentiate if you differentiate this bubble, you just get 3x squared. You see x squared, x squared. So try and keep an eye out for something being near enough the derivative of another thing. You see this bubble here is near enough the derivative of this. So me asking you to integrate this is me asking you to look for something in such a way that when you differentiate it, it gives you this whole thing here. So if you just concentrate on this bit here, if you integrate it, it's going to be one notch higher than this. So if you were to make this to be your initial guess, x to the power 3 plus 1, and then one notch higher than this, that would be minus 1. Now if I were to ask you to differentiate it, you would get this. The power will come down here, so that will be minus 1. And then the bubble stays intact. X to the power 3 plus 1. The power here gets minus by 1, and then you times the derivative of the bubble itself, which will be 3x squared. And then well, when you differentiate this, it will then give you this whole thing here. You see, this thing here is very similar to this, and then this thing here is exactly the same as this. So now make the adjustment to this. We want to negate this 1. So we want to negate this minus 1. So we would go back to here, make the adjustment, stick a minus in here. Now if you were to differentiate this, it will now give you, well, we'll get rid of this 1. But then we don't want this 3 here. So go back to your initial guess and make this to be your guess minus a third. And then when you differentiate this thing here, it will then give you, well, it won't give you this third here. So this now is now the exact same as this. Learn to do it just by glancing at it rather than using substitution. Well, integrate this, it will then give you this. Okay, because, well, integrate this, it will then give you this, or use whichever way you want. Use substitution if you want, but it's up to you. Integrate this, it will then give you this. So now as x gets bigger and bigger, as x heads towards infinity, put this into here. This thing here will be very, very big, making the whole denominator very big. Minus 1 divided by something that's extremely big is going to be 0. Now put 1 into here. So that would be, this would be 1, 1, 3, 3 plus 3, 6. So it'll give you a 6. So this thing here will converge. We now know that this thing will converge. So, hang on, going back to the theorem. There's a theorem that says that if this thing diverges, this will also diverge. If this converge, then this will also converge. Well, we've just established that this thing here is going to converge. So therefore, this will also converge. So the series here will converge. Okay? We don't know, it won't converge to a sixth, by the way. We don't know our mathematics is not good enough to determine the precise value of this summation. We can only, at the moment, we can only tell that we can only tell that it's going to converge. We don't know the precise value of this whole summation. We just know that it's going to converge. Okay.